Thank you for your attention. My name is Hugo Aerts, and I'm the director of the AIM program, so the AI in Medicine program. And in this talk, I want to talk about radiomics and AI imaging biomarkers in cancer. In this presentation, first, I will describe what AI-based imaging biomarkers are. Then I will show you some applications in cancer imaging, as well as some example studies that we are doing together with collaborators. So in this slide, you can see an illustration of a CT scan, for example, of a lung cancer patient. Now we can use AI to quantify this information that is contained within this image. So how we used to do this is that, say, for example, we want to quantify tumor characteristics, is that we worked with experts to implement different features that we thought that were important, like the texture of a tumor, for example. And we implemented these algorithms, and then after that, we built this classification models. So how we do this now with deep learning is that we do not have this feature engineering step anymore, and the networks learn automatically which kind of characteristics are important, both inside as well as outside of the tumor. So it really depends on what kind of data is giving to the deep learning network to learn from, that it then also will use as input and will determine what is important. So this is really the power of deep learning, because this is fully automated. So what is important there is that we think that AI will really impact the full radiological workflow from acquisition all the way to integrated diagnostics. So if we then focus on the image-based tasks, we think that AI will strongly impact the detection of cancer, so finding the cancer lesions. Then when we find cancer lesions, characterizing it better, both in volumetrics and shape, as well as other characteristics there as well, and then also as to monitor this over time. So these are the different steps that we think that AI will impact, and I will also show you some examples that we're doing in these different areas. What I'd like to show you first is a study that looks at X-ray images of healthy individuals and investigates if deep learning networks can quantify information in these scans that are related to survival of these people. So in a sense, we investigate if AI can quantify more relevant information than humans can. And as we are all aware, this can be highly relevant, as X-ray images are the most commonly used imaging test in medicine. So to do this, we use data from the PLCO trial of over 50,000 individuals, as well as from the NLST trial of almost 5,500 images. So what you can see here are the results of the model on the independent PLCO and NLST data. So the model gave a risk score from very low to very high risk. And based on this, we looked how well the patient did in each of these different categories. And we found a very high stratification power, both in the PLCO as well as in the NLST data, really demonstrating that even for healthy individuals, there's a lot of information in these X-rays that we can use, and deep learning is able to pick this up. So you might now wonder, it's like, great, but how do we actually use this? So for patients that underwent an X-ray for other reasons, we wanted to see, can we identify the risk of these patients getting cancer? And then should these patients potentially get lung cancer screening CT scan? So it's a very practical implementation. So for this, we only need input to data which is commonly available in the EMR system, which is a chest X-ray for whatever indication, age, sex, as well as smoking status. And an output was 12-year if the patient developed cancer within the lung cancer within 12 years. And we found in 2 independent testing sets very high accuracy that we could do this. So this is really a practical implementation, how such a system could monitor all the X-rays that have been taken in a hospital and say this patient you should actually refer to lung cancer screening because it is a higher risk. So, of course, we can also quantify established risk markers using AI methods. So one of the studies that we're doing there is that we're looking at coronary artery calcification, so CAC, where we all know that this is an important predictor of cardiovascular events. It can really guide primary prevention therapy, but also what is important is that it is visible on almost every chest CT scan. But it requires time and expertise and even special equipment to extract this. So we developed a deep learning system to predict cardiovascular disease, and by quantifying coronary artery calcifications. So we developed an end-to-end fully automated system that can analyze CT scan in under 2 seconds. This allows for identification of high-risk individuals in organized and opportunistic screening settings. And I want to show you some results, which I think is more important for the cancer field, where we apply the system to an independent data set of almost 15,000 individuals that were included in the NLST. So you can see a strong power for stratification based on the different risk groups. So very low, meaning that there's almost no calcium, to very high, to a high calcium load in these patients. And just to put it into perspective, these are the survival rates of the lung rats categories 1 to 4. So you can see it's almost a similar ballpark. So, these results really demonstrate the importance of looking at CAC in lung cancer screening patients. And the nice thing is that we can do this now fully automatically. Of course, we can also look inside of the tumor. So there's a lot of information that is available within the tumor region. We know that tumors are very different, and that imaging can capture this and can visualize this, and that AI can quantify this information in these images. So a study that we did about 2 years ago, actually, where we use a deep learning network to predict survival of patients. So only using information of the tumor, around the tumor, we wanted to predict how well these patients did. So how aggressive was that cancer, for example. And we did use a deep learning network to do this. And for this, we used several cohorts for training and validation. And we developed 2 different networks for patients that were treated with radiotherapy and chemo, as well as patients that were treated with surgery. And then looking at the results, we found for both the radiotherapy and surgical model very high stratification power in a high and low risk groups, where you can really demonstrate that there's important information in the tumor area that can be used for prognostication. So what you can see here is that it's a different illustration of the same results. So we're now looking at AUCs, so prediction for prognosis. What you can see there is that the deep learning models are outperforming all of the other data types, both clinical model as well as engineered features. So there's older methods that we used, as well as volumetric and maximum diameter. So this really demonstrates the power of deep learning. And it's also important to mention there is that the network did not require volumetric segmentations, only a simple seed point. So the network learned within the volume what was important of the tumor and what wasn't. And then looking at the heat maps, you can see here some 4 example tumors where you can look at the activation heat map. So what is the network looking at? And you can clearly see that the network also takes information outside of the tumor area into account for making this prognostic prediction. So also demonstrating again that there is important information outside of the tumor that could be useful, as well as inside, of course. To make it a bit more practical, we also developed a biomarker, an imaging biomarker to predict immunotherapy response. We published that last year in Annals of Oncology. So this is a data set of over 1,000 lesions in 203 patients with advanced melanoma or non-small cell lung cancer, and all of them were treated with immunotherapy. And then if you look on both on a lesion level as well as on a patient level, we found very high performance for our imaging model compared to, for example, volume as well. So what you can see here is that we can predict if a cancer lesion, if one single cancer lesion in, for example, the lung or the lymph nodes, we can predict the response of that one, but we can also do this in a patient level by integrating different cancer lesions, say this patient will respond to immunotherapy or not. Of course, there's a proof of principle study and further investigations are currently ongoing. But also, of course, we can monitor changes over time. So this is a study that we published last year where we investigated how is the tumor changing over time, and can we use deep learning to quantify this. And you see here examples of 3 different patients, both 3 pre-treatment images and then the first, second, and third follow-up. And what you can see there is the illustration of the box that was given to the deep learning network to predict response rates. So we used a CNN RNN combination to integrate that data for all the patients together. And here you can see the results where you can see that with adding more and more information into the network, your predictive performance increases. And also it's important to mention that each of these did better than the single time point alone, demonstrating the value of using more data for prognostication. Now the conclusions, I'm at the end of my talk. So deep learning can automatically quantify relevant information on an image, both inside and outside of a tumor. We can also use deep learning to develop fully automated risk prediction methods with high performance. But also it is important to mention that these methods not only help with improving speed and accuracy, but they can also be used for quality control to identify failures as well as individuals at risk. All right, I want to thank the following institutions and the following funding agencies. Thank you for your attention.